will tell us about that. Thanks.
Okay, thank you. I would like to start by thanking the organizers for giving me this nice opportunity to present our recent work on quantum computing and application with single photons. So, first of all, let me thank people who contribute significantly to the project. As you all mentioned yesterday, Jianwei is the director of our center, and Professor Sven Hoffling from Würzburg University grows and fabricate high-quality quantum samples for experiments. And we also collaborate with Xiaodong and Yao Wang on two-dimensional materials. And we have a team of very lovely students who are always willing or forced to, to push for better performance on single photon source. So in this workshop, we have already heard many excellent talks. In the workshop, started from the very beginning. And today we can even expect some real-world major applications of quantum communications. A much more challenging task is, however, quantum computing. Although the idea has been there for like 35 years, even before a lot of us was born. And there was serious efforts in the recent 20 years. But except from some mysterious D-wave machine, we still don't have working smoking gun machines that we can put on the table and compete with our laptop. So the field of quantum computing is less trustworthy if you compare to the name of this workshop. So building a universal quantum computer is challenging because it requires fault-tolerant control of a large number of qubits. So as a short term, we should also look for some non-universal quantum computers which demand much less resource, but can demonstrate quantum speed up for some specific problems, so as to give the community and also funding agencies some confidence. So to this end, probably the closed goal is photon sampling, because it requires only about 20 photons, and there's no headache for fault tolerance. So I will first briefly explain what is photon sampling. It's an analog of classical Galton board. So using quantum mechanically identical bosons or indistinguishable photons, will generate an output pattern that is totally different from the classical particles. And it turns out that predicting the output distribution of this multi-boson network is related to calculating the permanence of unitary matrix associated to the optical network. And this problem is Chao, which is in computer science scientist language is even more difficult than, for example, quantum factoring a very large number. So how about building exact quantum machine, including single photons, linear quantum network, and detectors to actually run the process? And so we have a race between classical and quantum. This is a rough estimation. So if we can build a 20 photon, about 20 photon photon sampling machine, the computational complexity will reach the level of the best commercial CPU today. And if we can build about 46 single photon sampling machine, and the complexity will reach 10 per second. Well, a few days ago we just have another news. This guy was beat by a new Chinese supercomputer called TYQI, the first. The new machine is 3 times faster, so we need 2 more photons. We need like 48, not a big deal. Yeah. So but controlling 20 photons is not easy, because intuitively, if you want to control 20 photons, all efficiency will scale exponentially as the efficiency of a single photon. And where are we? So this is the number of maximally entangled photons in the past in the past 10 years, 10 years, 15 years. Yeah, so, and this has been so far mainly achieved using spontaneous down conversion. In this process, we're showing UV laser, BBU crystals. There will be a tiny probability about 1 to minus, about 10 to minus 10. That one photon will split into two, and if you collect from the intersections, this will be entangled. So the problem of this process is that it is spontaneously emitted. So, so there's a probability of P that sometimes one pair of photons will emit it, sometimes no will emit it, and with the probability of P squared, there will be double emissions. And to do this for boson scalable boson sampling, these guys have figured out a very nice scheme that can overcome this probability, but still it will need photons with high collection efficiency and high indistributability combined. And in the past, we have achieved 6-photon entanglement, 8, and very recently we have just have the 10-photon entanglement. So the technical trick of this experiment is that we have a new design of this BBU crystal, so that previously the photons are collected from the intersections of these two rings into a single mode fiber, and the intersections is not necessarily Gaussian, so there's inefficiency associated with coupling into single mode fiber. And in this new configuration, the two rings, O and E rings, are separated in space, and these are, they inherit from the laser, which are naturally Gaussian. So, so we can achieve very high efficiency, about 80% efficiency of coupling into a single mode fiber, compared to previously about 40% to 50%. And we can also adopt this sandwich-like structure, so that, and with careful compensation, so that these two photons will be entangled. And using this method, with about with about 3 half-watt pump power, we can have millions of entangled two-photon counts. So this is very useful for the scattershot boson sampling approach. A more direct way is that we can, how about we don't like the probabilistic generation. So a more direct way is, can we generate some on-demand single photons in a push-button kind of way, so that every time it will generate one and only one. So this is a more direct approach to boson sampling. And to do this, we now turn our attention to single quant dot, single independent mass analytic quant dot. This is one photon amazing. So quantum dot field it's not a new field actually. Since the year of 2000, people have demonstrated photon anti-bunching from emissions of single photon source. But in the past, 15 years, people have only been doing experiments based on quantum dot of 2-photon experiments, and the problem of really applying this single photon source to do multi-photon entanglement, we need the source to fulfill the 5 checklists simultaneously. One is that it should have a very high quantum efficiency, meaning the energy is converted to electromagnetic radiation. And the second is deterministic generation, meaning push-button kind of way. The third one is should have a high purity, so that the high 2-photon probability is low. The fourth one is the photon should be quantum mechanically identical, so that they can do the 2-photon fundamental inference. And also, the photon, once it's generated, it should be collected and detected with high efficiency. Achieving this simultaneous actually is quite difficult. The predominant technique to excite and generate single photons is previously based on non-resonant excitation. meaning the excitation laser is in higher energy than the emitted photons. And the optical excitation first generate carriers in the quantum. It then relax incoherently into the lowest level of the quantum, then it emits single photons. The problem of this method is, as demonstrated in this paper, the two-photon interchangeability is limited to maximum about 70 to 80%. This is because of the uncontrolled time jitter from this incoherent relaxation. And the problem can become even severe when the quantum is embedded in a microcavity, so that the lifetime is shortened and the time jitter is comparable to the coherence time. And also another problem is in this excitation method, there's typically trade-off between single photon generation efficiency and the purity and the photon quality. So typically, when you increase the optical excitation power, so that the generation efficiency approaches to near unity, then the quality of photon will drop. And in the low excitation regime, the generation efficiency is always quite low. So to overcome this problem, we developed pulsed resonance fluorescence technique, and we excite the quantum not non-resonantly but exact on resonant with the energy of the two-light system. And this is a typical spectrum we can see from the spectrometer. This is the central very sharp feature is from the quantum emission, and this is the broad emission. The broad background is from the laser because pulse, so it's ultra short. This is log plot, and we can further improve the signal to background ratio up to about 500 to 1. And use this method, we can observe also the log oscillation in the time domain. So this is the simplest quantum optical model that we can treat the quantum as a two-level system, and we excite with resonant pulse laser. If we fix the laser power at this high pulse regime, so we can end up with a push-button single photon source. Every time we send in a high pulse, we will get one photon. We will generate one photon. This is the coherent control in the spectral domain, which is Fourier transform of the log oscillation in the time domain. And this gives us very optimistic signal that even some people think dirty solid state systems can have very clean atomic physics. So the main motivation to do this pulse excitation and the resonant excitation is to have high photon quality, and we did demonstrate in two-photon metal interference that now we can go beyond the previous 70 to 80% indistinguishability, and now we can reach about 97% indistinguishability. But the problem with the previous experiment is that because the quantum is embedded in gallium arsenide, which is a high reflective index material of about 3.5, so that without any chemical structure, the total internal reflection limits the extracted photons will be only to a few percent. So even the photons, the single photons are generated deterministically. They cannot be extracted efficiently. So to overcome this problem, we embed the quantum in a micropillow cavity with DBR mirrors in the bottom and in the top. And we can demonstrate Purcell effect, which is a reduction of the lifetime of the quantum emission from off resonant about 700 picoseconds to less than 100 picoseconds when it's resonant. And using this structure, we can efficiently funnel the photons out of the single photon device. And this is the log oscillation we published. So in the pipelines, every time we can, eventually detect about more than 3 million single photon counts per second. And now in our lab, downstairs, we have now reached about 9 megahertz per second. And these photon counts are detected by silicon commercial single photon detector, which have efficiency of about only 30%. So if we can have some high efficiency superconducting single photon detectors, we can climb this number up to about 20 million single photon count per second, which is, I think all these numbers are the state of the art, not only in solid state, but in all physical systems. And we further use the HBT interferometer to test the second order correlation of the single photons. You can see that in the zero delay, there's only less than 1% contribution of 2 photons. All the 99% of the contributions are 2 single photon sources. And this is, if you visit our lab, this is what you can see from our measurement program. And further, we test the fundamental interference of 2 photons, and we get about 98.5%. And in this experiment, the delay of the 2 photons was from the same quantum dot, and the delay is about 2 nanoseconds. So we further increase the delay of the photons generated and see, to what extent they can preserve the very high photon indistinguishability. And we increase up to about 15 microseconds, which means that about more than 1,000 photons are separate. We can even preserve 90 photon visibility exceeding 92%. So this means that if we excite the quantum dot with pulse laser, at least more than 1,000 photons emitted consecutively, they remain highly indistinguishable. And we can further measure the lifetime and the coherence time, T2 and T1, to quantify the degree of the photons and prove them to be actually transform limited up to about 90%. And this gives us a source that we can now scale the single photons from quantum dot to now we can do multi-photon experiments. So one path is that we can engineer many identical quantum dots, to be the same wavelengths, same bandwidth, and everything. The second, more easy and economical way is to have this one perfect quantum dot and actively demultiplex it into many photons. And now we have demonstrated even 1,000 photons they are all identical, so they can interfere nicely. And with this, we can demonstrate a real application of the single photon source. So we actively demultiplex the quantum dot and with tiny beam encoding, and we can send the photons into this loop-based network, which is equivalent to this network, a typical boson sampling network with variable ratio of beam split. And the beam split ratio can be controlled using this electro-optical modulate with electrical control. And with this source, we have now demonstrated 3 and 4 boson sampling. And the efficiency is now, the performance is much better than previous experiments with spontaneous Brown conversion. And with further refinement, it would be possible to do 20 photon boson sampling possibly in about 3 or 4 years. So the take-home message is that once the nearest term probability to show quantum supremacy might be through 20 photon boson sampling. And now we have, for down conversion source, we have now climbed up to 10 photon entanglement, and this should be quite nice to do the scattershot boson sampling, because except for its probabilistically generated, all the other parameters are now approach to the physical limit. And the quantum dot is now catching up, and we have now about 9 million single photon counts detected eventually, and they are transform limited. And we have also demonstrated a time being-based photon sampling. Actually, starting from this year, they have been very fast progress and also computation. From, you can see from this paper, our group and the group of Pascal and Andrew White in Australia. And so we have confidence that we can demonstrate quantum supremacy with photon sampling in the near term. So this is on the topic of quantum computation. And more, we can even have some wider imaginations. There's some science fiction movie called Star Trek, and when you are chased by some enemy on a planet, you disappear from a planet and reappear in another planet. So this science fiction was turned into some, on some level, turned into scientific reality by the six scientists. One of them is in the audience. And you can see also the citation is even twice than BB84 paper. Yeah. And not only this is very interesting, protocol to transfer quantum state. Okay, I will speed up. But also quantum calculation turns out to be a very useful component in quantum technologies like quantum repeaters, quantum computation, and so on. And so in the past, people have demonstrated quantum calculation in different physical systems, including photons, atoms, ions, convex centers, quantum dots, pseudoquantum qubits, and so on. But all the previous demonstrated experiments can only teleport a fundamental particle of 1 degree freedom. But we know even for the simplest case, a photon, an atom, we see has multiple degree freedoms. And we have recently, so teleporting a human is crazy, but if we want to move on in that direction, we should have more trustworthy calculation, which means we can teleport multiple degrees of freedoms. So in our experiment, we teleport the spin and orbit degree of freedom of photon, and we know that the most challenging part of calculation is to perform this biostate measurement. And for multiple degree freedoms, now we need to teleport, to do this hyper-entangled biostate measurement, which is for two independent particles. We need to control and project them into one of the 16th hyper-entangled biostate. And there are some previous theoretical papers, for example, by TYQI, and people previously thought that the unambiguous biostate measurement, hyper-entangled biostate measurement was impossible. So we overcome this problem by developing quantum non-dimensional measurement of a single photon and using this in-operator network. The most interesting part is that this non-dimensional measurement of a single photon is actually quantum calculation itself, because if there's a photon coming in, you can do this biostate measurement and teleport the quantum state away, and without changing any property of the quantum state. But if there is no incoming photon, we will have no click here, and we know that there is no incoming photon. So it's very interesting. Quantum calculation is not only, it's a very useful tool for calculation. So we have this calculation inside the calculation network, and we use 6 photon setup to achieve this experiment. And the method can also be scaled to even larger number of degree freedoms, from 3 to n degree freedoms. My time is running out, so I will speed up. We can also play with a few photons to demonstrate simple quantum algorithms. For example, recently for solving system of linear equations and also for dealing with vectors. And we also random walk a little bit to demonstrate from the two-dimensional materials, it can also emit single photons, which for the first time connect the field of graphene-like, graphene and beyond to quantum optics. And I will show some photos from our lab, which actually you can see downstairs. And with that, I would like to thank you for your attention. And this is a new journal launched, and I am editorial board, so I'm responsible for advertising. Thank you.
So we have a few minutes for questions. Okay, I'll start if nobody else has one. So the way I think about your single photon turnstile, I kind of think like a machine gun. You know, it's firing photons.
Yes.
And then, so you told the number of the parameters performance, but how many are blanks? What, like when you fire the photons, do you have a photon in every time bin, or are some empty?
So this is the first checklist. It's deterministic generation, meaning every pulse I send in, it should generate one photon. And from our measurement, the probability is about 98%. So it's a quantum efficiency of the physical system. But not all quantum emitters can behave very nicely, because sometimes the energy is converted to photons and other things cannot always convert it to photons.
Okay, but you have a 98% efficiency
yes.
with respect to the collector into that single mode. That's right.
That's the generation.
Okay.
So it's actually quite tricky. So every time we send in a pulse, the single photon needs to be generated, then escaped from the material, then collected into the single mode fiber. So there's a lot of challenges we need to address.
Okay.
So with your path 1 for your quantum dot source, what do you think are the prospects to be able to go to path 1? Means having many quantum dot sources and make the wavelengths the same.
Yes, so that's more challenging. So we now pick the less challenging and easier and economic way. And there's the challenge of the path 1. We have, first we need to engineer the quantum dot to emit the same wavelength, because the self-assembled quantum dots, they are inhomogeneous, meaning the wavelength distribution is random within about 40 nanometers. So it's very random. And people have demonstrated to use electrical field to tune the wavelengths to be identical, and the tunability should be sufficient. And the next, we need to, for each device, we need to embed them into micropure cavity. So the resonance should also be identical, and also the bandwidth of emitting photons. So the path 1 is more challenging, but the advantage is the repetition rate can be much faster than the path 2, because we can have multiple emitters, and the repetition rate can be, for example, if you want to do 20 photon experiment, can be 2 to 3 orders of magnitude than the path 2.
Okay, and we have a last question.
Yeah, sure. So,
wait for the mic.
I have just a very simple question. So you can generate one single photon per each time, right?
Yes.
So can you generate the photon pair, like entanglement photon pair, for each time? Like if you add some further things.
So there's mainly 2 methods to generate photon pairs from quantum dot. One is to use the biaxial decay. So there's biaxial level and the 2 axial level and the vacuum. So you can use this decay channel to generate single photon, entangled photon source. The second approach, which you can read from a paper from arXiv yesterday, is that to explore the idea of cluster state machine gun, which was proposed by TYQI2016 and another his colleague. And I think Israel group have demonstrated some preliminary data of the cluster machine gun. So the idea is is very elegant. So you have these two-level systems, and you can control the ground state coherence, and you can send some pulse. It will emit a string of cluster state, which is not limited to 2 photons but to n photons. It's very nice idea. Yeah.
Okay, let's thank Chao for a great talk.
Thank you for attention.